So looking at page 79, number 4, it says, write the triple integral related to this function f of x comma y comma z equals 1 with the constraints that x, y, z follows the model of x squared plus y squared plus z squared equals 9, which is the equation of a sphere with a radius of 3. So this is a sphere. And we have a radius of 3. All right. And then we would evaluate by converting to cylindrical coordinates. All right. So first things first, we can establish that it is going to be a triple integral of the function f of x comma y comma z, which we're establishing is 1. It really is just a question of, all right, so what are our constraints, beyond just the x squared plus y squared plus z squared piece of it, equals 9. So what I could say is that I'm going to anti-differentiate with respect to z first, then y, then x, for no particular reason other than that's what I want to do, right? At least at this point, right? So we're going to possibly modify that thinking as we go forward, but just, it kind of feels like I shouldn't open an integral without putting a integration variable involved in the appropriate place, right? So let's say, for example, I am working with the variable z first. If that's the case, and we know that x squared plus y squared plus z squared is equal to 9, we could solve this by, subtracting the x squared and the y squared. So z squared would be equal to 9 minus x squared minus y squared. And then taking the root, square root of both sides, it's just a question of whether or not we want the top half or the bottom half or both. Right? So if we work with the positive one, then we're only taking the top half of the sphere, so the northern hemisphere. Right? If we take the bottom half, then we're getting, if we take the negative, we're getting the bottom half, which would make sense. If we integrate from the negative radical to the positive radical, that would give us everything from the bottom piece, the bottom half to the top half. Right? But what we could also do is kind of break this up into more reasonable components. Right? So again, we know that this is the same as saying plus or minus, but we also know that a sphere is fully symmetrical. So if I find the volume of the top half of the sphere, then all I have to do is double it. Right? So that allows me, I'm just working with the top half, to take this whole expression here, or the equation, but then just drop the plus or minus. All right, so then what that would say is that I would be chopping this. Let's see if I can get my Geogebra to work right. I would be chopping this off at z equals 0. Now that's not the most lovely looking diagram ever, but hopefully you get the idea. I can also try to change the color. I'm going to go, I guess that works. Sort of. All right, so I'm chopping it off at the equator, essentially. All right, so what we would be getting here is the volume bounded between 0 and, so that horizontal plane, z equals 0, and the top half of the surface. All right, so that would be my first set of bounds. Just move this over because we know we're going to need a little bit of room for this. So 9 minus x squared minus y squared. All right. Now, in terms of the x and y constraints, well, it's not a rectangular set of constraints, so it's not a matter of saying that we're going out to some constant in x or some constant in y, both of them, being constant. It's one of them may have constant bounds, but the other one is certainly not going to, because it's not a rectangular base region. Right? So what we're going to have to do is break this down into the xy plane by setting my sphere equation, or setting the z value of the sphere equation equal to 0. All right, so x squared plus y squared plus 0 squared is equal to 9, so this is in the xy plane. Now, the only reason we're going for the xy plane here is because that establishes the extent of the bounded region. All right, the furthest reach of that bounded region seems to be on the xy plane. That's the furthest we get from 0, 0, well, 0, 0, 0 in this case. All right, so we're looking at x squared plus y squared is equal to 9, which represents the equation of a circle with the center at 0, 0 and a radius of 3. All right, so what I'm going to do here is solve that for y in terms of x. All right, so y would be equal to, or well, y squared anyway, is going to be 9 minus x squared. If I solve for y, so if I take the square root of both sides, I could get y equals plus or minus the square root of 9 minus x squared. Now we have that other, well, not other, but really the same predicament we had before, which is to say it's a matter of, do I want to work with both the positive and the negative radical, or do I just want to work with one of them? You know, what am I doing here? So what I'm going to do is plot this. I'll use Desmos. So I'm going to plot, I know if I plot the circle, I'm going to get the whole shebang. But if I plot just y equals, when I say circle, I mean x squared plus y squared equals 9. So if I plot the square root of 9 minus x squared, I'm only going to get the top half of the circle. All right, so in the work that we've done so far, we've kind of established, and this is going to be kind of a crude diagram here, but just kind of bear with me. We already know that we're getting, that's pretty ugly is what I meant to say. Okay, I mean, it's hand drawn, but it's still a little bit better than the trash that it was previously. All right, so this is what we were getting with the positive square root for the sphere equation. All right, now if we look at just the xy plane component of it, it's still circular, but now we're only getting a portion of that, the northern hemisphere of that circle, and you wouldn't even call it a hemisphere at that point. You would just call it a semicircle. All right, so I have this diagram. I can just do lickety split here. I am shockingly capable of drawing a circle sometimes. All right, so we want to be just thinking about whether we want to go with just the positive or take the span between the negative radical and the positive radical and use that as the bounds for our y integral. There's pros and cons either way. All right. If we had to evaluate this by hand, and we will, but using polar coordinates, then we do have to figure that part of it out in terms of substitutions and cleaning up the algebra. But if it's a matter of just writing the integral, you know, there's no sweat. You know, just put in a negative radical, put in a positive radical, make it as ugly as you want, you're fine. Right? But you know, we want to make it as user-friendly as possible. Right? So what we need to do is think about what this represents in terms of the entire sphere. All right. So now this is going to be brutal in terms of my ability to draw, but if we assume this is the x-axis and this is the y-axis, then what we're looking at is this portion of the circle. It auto-corrected on me. Right. Now, it should go out to the furthest extent of the sphere, but it's not happening. All right, so, and actually it should be a radius of 3 anyway, so I guess I should try to at least make that sort of look the part. All right. I'm going to try to draw. All right, so we're only getting this part of that circle instead of the whole thing. All right, now it's not a good perspective drawing to say the least, but that's where we're at this point. All right, so it's the top half of the sphere, but only half of the top half of the sphere. All right, so we're getting a little wedge shape cut out of this whole thing. All right, so that's what this corresponds to. So this piece here corresponds to that. Knowing already that we're working with half of the sphere because we chose the positive root over here, we're now chopping that half in half again by working only with the positive radical over here. All right, so what that tells me is that what we're going to need to do, if we want to avoid having a negative radical in here, is make this go from 0, ooh, that was pretty ugly, 0 to 9 minus x squared, but we now have to quadruple this. All right, we have to quadruple it because the half of a half is going to give you a quarter of what the true volume really is. All right, so then what we need to do is determine the bounds for x. That's actually the easiest part, because now that we've restricted y to be any value that satisfies the relation of the square root of 9 minus x squared, then we just need to know any possible x value that's within the constraints set forth by the sphere. But it also happens to be the case that the domain of this function, the y equals the square root of 9 minus x squared, which is negative 3 to 3, is consistent with the most extreme x values in the sphere. So we would be going from negative 3 to 3. All right. Now, what some people will do, just because they want to make things a little bit more convenient, and the convenience comes into play when you're talking about really doing stuff like this by hand, evaluating it by hand. You might consider, okay, well, what if I didn't go from negative 3 to 3? What if I went from 0 to 3? So start here and go to 3. Now, this is going to be a terrible perspective drawing, but you'd be looking at just this portion of it. So we started off with half of a sphere, so we're in the top half. Then we split that down the middle because we're only living in the first and second quadrants of the xy plane. Then I split that in half again by only going from 0 to 3, in which case I would only have the first octant, so I would multiply my final result by 8. All right, that part is up to you, because once you get to this step here, the act of integrating with respect to x, you're dealing with constant bounds. Right? So that's all calculator work anyway. So it wouldn't begrudge you leaving it as a negative 3 to 3, but you could manipulate it further if you wanted to. But at this point, you'd be looking at this as being an appropriate, one form of an appropriate integral, triple integral, to give you the volume of the sphere. Okay, so next up we're going to be looking to evaluate it by converting to cylindrical coordinates. So now we're going to try to evaluate this using cylindrical coordinates. All right, so what I did, just to kind of give a better visual, is I took some time and I developed the Geogebra to try to kind of do a little bit better of a job than my terrible drawings could do. So this would be the entire sphere. All right. If we only focus on the top half, all right, so just this piece here, just focusing on the top half, it obviously gets rid of the bottom half. Now, if we look at the radical and only focus on the positive radical, that brings us to the interval going from -3 to 3 for x, but only 0 to 3 for y. So that basically the top half, if you were to look at it from this perspective, oh, wrong perspective, this perspective. And it doesn't want to stay. Okay, I'm just going to hold it there. I'm going to long pause for a second so you can just kind of absorb what I'm trying to say. All right, so that's the top half of the circle. Now, what I was saying is that if you wanted to, you could truncate it even further by saying, well, maybe I don't want to go from -3 to 3 in terms of x. Maybe I only want to go from 0 to 3, in which case you get this. And from there, what you can do is say, okay, well, what fraction of the overall sphere am I going to get as a result? 1/8 of it, because you're only in the first octant. So as long as you know to multiply your final result by 8, then you're in good shape. All right? But what we did was we left it off like this, knowing that all we'd have to do in order to get the correct volume is multiply our final evaluated iterated integral by 4. All right, so the next step in our approach to doing things here is going to be to convert it over into cylindrical coordinates, bearing in mind that this is going to drastically affect the bounds. All right, so in some ways it's going to be great news, in other ways it's going to be complicated. All right, so first things first, z is equal to z in cylindrical coordinates. All right, so there's really nothing we can do about the dz part of it. All right, so I'm going to reproduce this. Put it on down here, get rid of all this. All right, so we're stuck with that, but I can replace this with its polar equivalent, all right, because we know that x squared plus y squared is equal to r squared. This is the same as saying the square root of 9 minus x squared plus y squared. So we're looking at a new set of bounds that would go from 0 to now it's not x squared plus y squared, it's r squared. So 0 to the square root of 9 minus r squared. All right, so that takes care of this piece. Now we know that dy dx in rectangular coordinates is analogous to r dr d theta in polar coordinates and cylindrical coordinates. I'm going to make a substitution there. All right, so this is a product. We'll have to account for that in a sec. Now, as far as these bounds are concerned, I have to account for the y bounds and the x bounds, but now I got to think of them in terms of r's and thetas. So just looking at the entire circle, you might want to rethink the process here, but if you're just looking for a reproduction of what we created in this triple integral in rectangular coordinates, we have to go back and think, okay, well, what did we get? We had a circle that had a radius of 3. All right, this circle has a radius of 3. All right, so in polar form, we'd be spanning, let me get that, copy. if I want to cover the same space, I'd be arcing my way out from center with circles having radius of 0 all the way to circles having radius of 3. All right, so that's nice. So 0 to 3. But I wouldn't be going all the way around the circle. All right, I'm only going to go from 0 to pi. All right, that's going to cover the same amount of the circle that we did by going from 0 to radical 9 minus x squared and then negative 3 to 3. All right, so I can pop that in, 0 to 3, 0 to pi. Now that radical 9 minus r squared is still only related to the top half of the sphere, all right? Because that came from this. We ignored the bottom half. We ignored the negative. So I'm still looking at something that's going to be exactly 1/4 of what I need it to be. So I'm still going to have that 4 out in front. But now I'm looking at something that's going to be a lot easier to work with, all right? So I got to clean it up a little bit. At least in this first step, there isn't much cleaning to do, but it's still necessary. All right, so I got an r times 1 is r, dr d theta. All right, oh, sorry, I lost my z. All right, so the first step in the process going forward is going to be to integrate with respect to z. So that r is treated as constant, so we're looking at rz over the interval of 0 to the square root of 9 minus r squared. All right, so that's going to become, fortunately it's not too crazy in terms of substitution, r root 9 minus r squared. We still have the 0 to 3. We still have the 0 to pi. Still have the 4. Still have the dr d theta. All right. Now, the good news is because it's in polar coordinates and everything's in terms of r, it's really not too bad to work with. Because if we want to, we can go right to the calculator now. And it's just a question of how much you want to. You know, I really want to. You know, because I'm looking at all this work we've done for this one problem, and I'm saying, you know, I think I'm worked out here. So 0 to 3. X rad 9 minus x squared. I'm using x. Dx. All right, so it's clean 9. It's pretty nice. So this whole shibiggity bangity boomity boom here boils down to just a 9, which we're going to integrate over the interval of 0 to pi d theta. Now you could have used u substitution there, but I'm actively discouraging you from doing stuff like that. You've already been assessed on that. That was Calc 2. All right, so we have 4 times, and this is going to be 9 pi, 9, well, it will be 9 pi, but 9 theta first over the interval of 0 to pi. And so we're looking at 4 times 9 pi minus 9 times 0, so 36 pi.